So the variation of in time, how does it reflect in frequency domain, is roughly same, whether it be with discrete time Fourier transform, or let it be with another transforms like jet transforms or other Fourier transforms in fact. So, and many of the properties, other properties, how does say some of the say multiplication in time domain reflects in frequency domain and so on. Many of the properties are roughly similar, almost similar, except that there are minor differences based on the exact framework, whether it is say discrete time Fourier transform or jet transform and so on. So the properties that I discuss in this video lecture, okay, will not be discussed in full detail when I discuss about the jet transforms. Okay, so it is expected that you understand fully what I discuss here, and you will be able to do yourself tell what happens in say similar kind of when the similar kind of properties are to be looked at, what happens in that transform like jet transforms and so on. You should be able to derive yourself or tell yourself. Okay, that is expected. So we will start the discussion. Yeah. So now tell whether you are able to see the screen or not. Are you able to see the screen?
Yes, sir.
Yes, sir.
Right. I suggest all of you to mute your microphones unless you are answering. So, so I hope you should have looked at the previous video lecture. So I am moving on to the new topic now for the discussion. So let us say, assume that we have a signal x of n, okay, a discrete sequence or signal x of n, and its Fourier transform, okay. Here discrete time Fourier transform is x of e power j omega. Okay, so how are they related? You know, right? So x of n e power minus j omega n, n varying from minus infinity to infinity. Okay, so this is the what is essentially doing is we are trying to find the correlation of sequence x of n with the complex exponential, okay, discrete complex exponential sequence with frequency omega, and that is captured in terms of the frequency content or discrete time Fourier transform. Okay, so as discussed in a speech processing course, those who are there, this correlation can also be looked at as the projection of the complex exponential sequence on the sequence. Hello? Are you able to hear or not? Hello?
Yes, sir.
Yes, sir. We are able to hear you.
We are able to hear.
Right. Question? Some of you were asking something? Okay. Also, if so, this x, the frequency like representation or x of e power j omega can also be looked at as the projection of the signal x of n on the exponential sequence with a particular frequency. Okay, so if you just say the correlation as we see in vectors. Similarly, the correlation can also be, say if you have a vector, say x here and a vector y here. Okay, so so what we said previously, this is, say in some sense x transpose y gives us the similarity. That's what we said. Okay, that is referred to as like that is obtained through correlation. This can also be considered as the projection of vector y on x. Okay, this also gives in some sense the similarity. Okay, so both are equivalent terms. So I would like to connect for those who are taking the speech processing course, would have had their discussing this as the projection of exponential sequence onto the sequence x of n, or the projection of eigen functions or eigen like the basis functions onto the x of n. So exactly what the same is what we are discussing here. So you can think this as the projections of x of n with different frequency exponentials. Okay, so similarly now the inverse for a transform x of n, when you wish to write from x of e power j omega. Okay, how do we write? How do we write? E power j omega n. What integral is from where to where?
Minus pi to pi.
Minus pi to pi 1 by 2. Okay, so this, as we are explicitly denoting with x e power j omega, this is periodic with 2 pi. Okay, and thus we are taking over one period while writing. This can also be looked at the correlation of the frequency content with respect to a particular sequence x of n, a particular instant. Okay, x of n with varying frequency. Or so because this correlation is now done in the frequency domain rather than in the time domain. Okay, so previously, see, this indicates in which domain that correlation or the projection is done. Okay, so here this is done in the frequency domain. So particular n, we are trying to see the correlation of the exponential signal with like particular n with varying frequencies with respect to x of e power j omega. This can also be considered as the projection of the complex exponential with the spectrum. Okay, x of e power j omega. Fine. This can also be considered as reconstructing from the projections that you have taken here. How do we reconstruct the signal x of n? Okay, so it can be considered also in that way. So if we have different projections for different frequencies, how do we use all these frequencies put together and reconstruct x of n here? Okay, I hope this kind of understanding and analogy is also clear. Right? Is this clear?
Yes, sir.
Yeah, right. So now let us see some of the properties of discrete time Fourier transform. See, there are different things that usually we need to discuss. Say, properties are, say, in some sense, if there is a variation in time, okay, if I delay in time, okay, what will happen in Fourier domain, okay, in the frequency domain, okay, that is one kind of properties. Okay, if the signal has some nature, if it is real or if it is even and so on, what will happen to its Fourier transform? Can we conclude or infer better in frequency domain? That is the kind of the properties that we discuss. Okay, so when we start discussing this, so x of, say if we just delay the sequence in time, okay, what will happen in the frequency domain? So I think some of you know already. How do I, what will happen and how do I derive?
No, you have already given examples, sir. X of del of n minus n naught.
No, I don't want to take the example.
Okay.
So how do I derive in general? Okay, and then what will happen? Give some clues on it.
Sir, in the frequency domain, it is multiplied with the exponentials.
Okay, it will be multiplied with some,
j
okay,
omega naught.
so it is multiplied. So, but we need, you know, you tell me the procedure. How do I get that? So you'll fill that. So what should I do to know what will happen in frequency domain?
We have to come
The
from
summation.
Yeah, I should just go by the definition. Okay, from the definition I can derive what will happen. Okay, so I just want to find Fourier transform of x of n minus n naught. Okay, so hope this is clear, right? So now I will just try to write. Okay, sorry, summation we have to write, right? Yeah. So summation x of n minus n naught, okay, into e power minus j omega n. Okay, for many of the basic like properties to derive, definition is usually very helpful. Sometimes forward definition, this is useful. Okay, sometimes the like inverse definition or the say x of e power j omega to x of n definition is useful. Okay, so here n is equal to minus infinity. Yeah, so what do we do now? Simply, what do we do now?
Limits change.
Yeah, variables. Okay, n minus
X of
n.
n.
Okay, then x of k into e power minus j omega k plus n.
N minus n. Okay.
So here I have put k equal to n minus n naught. Okay, that implies n equal to k plus n naught. Okay, that's what I have substituted here. Fine. I hope this is clear. Those who have not seen this many times before now in recent times. Okay. So this is equal to, so summation k equal to minus infinity x of k e power minus j omega k into e power minus j omega n naught. Fine. So this summation is over which terms here? There are three terms here. Summation goes only over
middle terms.
yeah, only
K
these
times.
essentially can be written as finally
x of e power j omega into
yeah. So right, what is this one? X of e power j omega. Okay, because either summation is over k or n doesn't matter. If it is minus infinity, that is fine. Okay, because I think as you can see, n going from minus infinity to infinity makes k also go from minus infinity to infinity. Okay, so now this is equal to x of e power j omega into e power minus j omega n naught. Okay, so here what should I fill? Minus j omega n naught. Okay, fine. So what is its effect? So if there is a delay in time domain, okay, that means if you are delaying the signal in time domain, okay, then what is happening in frequency domain? Can one of you tell verbally? Yeah, tell quickly. One of you tell what's happening here.
yes, sir.
In
Multiplication with the exponential in frequency domain.
Yeah, that is fine. But what is this multiplication with exponential causing?
Change in
Frequency
phase, sir.
shift.
Frequency. Okay,
Shifting.
it is not frequency shift.
Phase carrying some other phase.
Oh, it is happening on the
Phase.
it is on the phase. So what is happening to phase? What is happening to phase? Say if x of e power j omega, okay, can be written as amplitude of x of e power j omega, okay, into say phi e power j phi. Oh, phi. If I am able phi of omega, I will write phi of omega. Okay, if I write like this, x of e power j omega, if I write like this. Now, what is this? Say e power minus j omega naught n naught into x of e power j omega does for this x of e power j omega. Now you should be able to see very clearly and tell. What does this imply here?
Sir, it's the delay in the time domain is adding a phase of omega and naught, minus omega and naught in the
Right.
frequency domain.
Right. So what is the implication here? Phase delay. Okay, delay in phase. Okay, phase delay by corresponding amount. Okay, omega n naught. Okay, so delay in time by, for example, here as n naught, phase delay by omega n naught. Fine. Is this clear or not? Okay, this also can be considered as modulation. Okay, so because this is a, if you just write in terms of real and imaginary components, this will be cos omega naught, omega n naught minus j sin omega n naught, right? So you're multiplying with cosine and sine signals within frequency domain. Okay, so this can also be considered as in some kind of modulation to this spectra. Fine. Is it fine or not?
Yeah, fine, sir.
Yeah, okay. So now let us move on. Okay, so now let us take e power minus j omega naught n, okay, into x of n. Okay, let this be our initial time domain signal, and we want to know what is its discrete time Fourier transform. Okay, so what are we doing here in time domain? Multiplying with e power minus j omega naught n. What does it causes to the change in the signal x of n?
In the frequency domain.
Huh?
Shift in the frequency domain. Time
That
shift,
is,
frequency shift in the frequency domain.
yeah, it does frequency shift. Some of you are telling. We will see actually how does it shift. Okay, so omega and so on. We will write what it is. Okay, but what will happen in time? What is this in by words, or what does its implication in time domain? Just multiplying with e power minus j omega naught n means what in time domain?
Phase delay, sir.
Phase delay, sir.
Yeah, so if x of n in fact is a complex number, okay, is equal to mod of x of n, signal at different e power minus j phi of n, for example, here. Okay, so in that case, what will happen? There will be delay phase in phase because of this. Okay, so this is one thing, or we can also consider this as modulation. Okay, so this implies, okay, this effect as phase delay in time or modulation. To x of n. Fine, is this fine? Okay.
Yes, sir.
Yeah, and now let us see what is its implication in the frequency domain. Okay, so here I am deriving with few details, hoping that you will be able to easily catch the procedure or the way in which we can derive. Okay, if there is some change in time domain signal or some variation to the time domain signal that we considered as standard, that can be related to standard signal x of n. Okay, how do we find the frequency, like implications in frequency domain? Okay, also you will be able to extend later to other like transforms. Okay, so now where should I start? X of, so I will start here. Say I will denote this as say x 1 of n, let it be. Okay, if this is x1 of n, x1 of e power j omega I will write. Okay, this is not exactly x of e power j omega. Okay, x1 of e power j omega, or if you, even if you wish, you can also write, okay, so y of n as well. So I'm just writing x1 of n, it's fine. Is equal to, how should I write here? We again go by expansion. So so in fact, in usual classes, I usually recommend you people to do it yourselves, okay, rather than I doing. I will give few minutes, and no, if you are not, if you are stuck at some point, I clarify that. So if you have pen and paper, you can quickly work out these things. So I will probably do parallelly, but you can do here at your places. So just check what I'm writing is correct or not. Is this fine? So we will write it.
Yes, sir.
So I think this is equal to
Minus infinity to infinity.
n equal to minus infinity infinity x of n e power minus j. What can I write? How can I write this better? Is simpler. Okay? Because both are in exponential. So this is nothing but what? This is nothing but exactly like x of e power j omega. E power j. What should I write here? Omega plus
Omega naught.
omega. Okay, so if I keep positive sign here, then minus sign will come there. Okay, so that's okay. If I write with positive sign here, then minus sign come here. Okay, so I think that's clear to you. Fine, right? So
Yes.
so what happened in frequency as an effect? What is its implication in frequency domain?
Advancement in frequency.
Yeah. So if there is a phase delay here, there is advancement in frequency. So I would say or shift in frequency. Okay, in frequency domain. Is this fine? Is this clear?
Yes, sir, clear.
Yeah. So then we will discuss other properties. So let there be n times. So we will anyway start in next space. So let this be our now signal. Okay, sequence. What is discrete time for a transform we want to do? Okay. So let this be again x1 of n if you wish. Okay. So now where do we start? We will suggest. I want to find out what's its effect in if I'm multiplying by n. What does it? How does it affect in the frequency
Differentiation
domain?
in frequency domain, sir.
Yeah, it will be differentiation in frequency domain. Okay, but we would like where
Minus
should
j d by d omega.
okay
Minus j d by d.
j into okay. So where should I start for derivation of this? So how do I start for deriving this result or finding this implication? Can one of you quickly tell? Where should I start?
Frequency domain, sir.
So by definition.
Yeah, by definition. So by definition of from frequency domain, it will be simpler. Because this anyway is very clear. Okay, so x of e power j omega, you can write, sorry. Okay, fine. So in fact, we are not starting in frequency domain. We are just writing the definition. Now what we do? we just try to differentiate. Okay, because this anyway will give minus j. Differentiation is with respect to omega. So n into x of n into e power minus j omega n. Okay, so here you can multiply both sides with j. Is this correct? Okay, so this is nothing but Fourier transform of n into x of n. Okay, so if this is simpler, because anyway we can see what will happen, the differentiation in the frequency domain, that will lead to multiplication with, okay, n times x of n. So what essentially is happening is, so we are multiplying with the sequence, okay, so that is making the frequencies differential frequencies identified. Okay, fine. So we'll move on to the other properties. So which are the other properties usually are of importance? So if you multiply with time, like two functions in time domain, or convolve two functions in time domain.
Multiplication frequency domain.
Multiplication in the frequency domain. So how it is? Right. Yeah. Is this fine? And if there is a multiplication in time domain, what will happen in frequency domain?
Convolutions.
Yeah. So all these things can be derived quite simply, okay, from using the definition. Okay, so in fact, since these are all applied in all transform domains, these are and the definitions are also almost similar. They do apply in all transform domains. Okay, so convolution we can write, or otherwise we can write explicitly. Okay, so so how do we derive this? Say if I want to derive this, for example, first one. So if you want to derive this, how do I derive? How do we derive this? So we can derive in both ways. You can take actually here a convolution you can write explicitly, and then you can show that you take Fourier transform for it and show this. Okay, that is equivalent to this. Or you can take these two, okay, in the frequency domain, expand them and then take again the inverse Fourier transform and do it. Okay, so we will take the say let this be y of n. So we take y of e power j omega. We try to write y of e power j omega, which is y of n. See, what is better is, see, these are all you might have done already, many of you. Those who have not done also, since the idea is given now, how to do prove these properties, I suggest don't again refer to my video lecture. Okay, you just like try to just figure out what are the properties to be proved. Just list them and then start deriving yourself. Okay, that is the best method or better method of understanding this. Okay, so what is y of n? It is, say, over k. x of k h of n minus k into e power minus j omega n over n. This summation is over n. See, when you have more terms, you should be very clear on summation is on what. Okay, on k, rn, and so on. And this is. So what do we do now? One of you can tell. So how do I simplify this better? Yeah. Are you there?
Yes, sir.
What do we do now?
Good thinking, sir.
To simplify this, what should we do? No answer? How do I simplify? No, I am not listening anything. From here, how do I proceed? What is the next step? Kartikeya, will you answer?
Sir, this h of n minus k into e power minus j omega can be written as the transform of h of omega, h of n.
Yeah, you make. Okay.
Yes, sir.
You put. Okay. So then this here, k x of k. Okay, into this now or m we can write h of m. Okay, into e power. So we would like to write, because what we want to write is we want to write in the form of Fourier transform. Explicitly, we would like to get the discrete time Fourier transform expression for h. Okay, so so this can be written now as n equal to, this implies n equal to m plus k. That we'll write here, minus j omega m plus k. Right? And here, now we can write this as summation k x of k, and here we can split e power minus j omega k and summation over m h of m e power minus j omega m. Okay, so what is first one and what is second one?
X
This
of e
one is,
power j omega and
yeah,
h of e power j omega.
and
H of
this,
e power j omega.
yeah, h of e power j omega. Okay, so this is essentially equal to x of e power j omega into h of e power j omega. Okay, so what does it tell? It tells that if you are multiplying in frequency in one domain, okay, the implication in another domain is in terms of convolution. Okay, so multiplication means only element by element things will happen. See, if you have two signals like this, okay, so multiplication in time domain means what? Only element by element things will happen. But in another domain, what will happen? So you're understanding what's happening in, say, are you able to visualize what's happening? If there is a signal, discrete signal like this, okay? Okay, if there is another discrete signal, something like this. Okay, something like this. So let this be 0. So if you're multiplied here in time domain, what is happening? So multiplication I am denoted with dot star. Only element by element operations are happening. That in one domain is implying in some sense, okay, convolution means what? Let this be the spectrum for one and let this be the spectrum for another. Okay, so ranging from 0, okay, maybe 0 here. Okay, something like this, and minus pi to pi or whatever. Okay, so what in another domain, what is happening? Almost it is convolution means one is like
Frequency reversal and multiplication.
Yeah, multiplication. So it is the aggregation of several frequency components are giving one particular, okay, one particular time domain output. So this output at this instant is obtained here by aggregation of some information here to here. Okay, it is not simply by like here element operations relates to a convolution kind of operations here. Okay. Okay. So you can similarly derive the other one. I am not deriving it. So what else are left in terms of this kind of properties? There is one important
theorem.
theorem. Okay, so what does it tell? Summation over Rx of n, no n, neither is fine, is equal to what?
1 by 2 pi.
1 by 2 pi.
Yeah, 1 by 2 pi as an normalizing term. Yeah, energy in time domain and frequency domain are same. Okay, so because this is periodic signal, we consider power. Okay, and since this is a periodic signal, we consider energy. Okay, our energy density we can consider it as. So this xk whole square is referred to as energy density. Okay, this is also in frequency domain at a particular omega, at given omega. Okay, so how do we prove this? How do we show this? So any thoughts? Yeah, can one of you tell or not? So we can take the frequency domain thing. Okay, it can be done in either way. Okay, so if you take this, so 1 by 2 pi, okay, integral minus pi to pi. So how do I write this? X of e power j omega into x of, so mod whole square, any complex number mod whole square can be written as e power j omega. Correct? Is this correct or not? So x into x star is nothing but mod square. Okay. So now how do I expand this? 1 by 2 pi, integral minus pi to pi. So how do I expand x of e power j omega here? Because I need x of n. Okay, x of n e power minus j omega n. Okay, I have written like this. Summation over n. What should I write for this? What should I write for this? Some answer
Whole
is expected.
conjugate, sir.
Oh, yeah, whole conjugate,
Whole
fine.
conjugate.
But is it n or something else should I consider here? Can I write with n?
Yes, sir.
Oh,
Yes, sir. You can
if I write
write
with n, then we'll get confused, right? We'll mix it.
Yes.
So this is summation is only on this. This summation is not on this. I would like, do I need to separate them or not?
Yes, sir. I use another variable m.
Yeah, we should use or we can use. No, we can use n itself. I need clear answer here.
We
Any
should,
variable
sir.
is fine or,
use, sir.
is the
We should
same
use.
variable is the question. Is the same variable or different variable should I use?
Different variables.
We should use.
Yeah. Because this summation is only over this summation is only over this. Okay. Whole star. Okay, d omega. Okay. So when I trivially show like this will be very, this look like quite trivial. But when you do, each of these things will matter. Okay. So whether you consider this or not, okay, which one is easy to derive also matters sometimes. Okay. So it is not equally tough. Okay, in some cases, in this case, for example, If you just take in time domain, it is not that easy to show. Okay, but if you take frequency domain, because from the definition itself you can go. Okay, because this operation can be done from definition. Okay, wherever you can go from the definition, better take that option. Okay. Yeah, this is in some sense, yeah, multiplication with the ramp kind of thing here. Yeah. Okay, so here this is summation over n, summation over m, okay, x of n and x star of m, right? Okay, I'm writing now both together. And what should I write here? E power minus j omega n. What should I write here? E power j omega m d omega. Correct? So please see, I have written star also. So I just mixed them. Okay. So what is this? 2 pi. This should I keep this integral here only? I can take further inside. This integral is over what? On which
Over
variable?
omega, sir.
Yeah, on omega. Out. Okay. Summation over n. Okay. X of n. Okay. X of x star of m. Okay. Into integral. So if I want, we can take even this 2 pi also here. Okay. So 1 by 2 pi integral e power minus j omega m minus n into d omega. Can I write like this or not? Okay. What is its answer? What is this integral? What is this? Yeah, I need quick answers from your side. Otherwise, this is as good as sending video lecture. So what do you think is this? Niharika?
So it will be 2 pi into,
Hmm.
it will be area of our
Okay, area over any other student?
1 for m not equal to n, otherwise 0 if m is equal to n, sir.
Oh, this is 0 if m equal to n, is it?
No, sir.
Yes. Then clarify.
I think that all.
0 for m not equal to n, sir.
Yeah, 0 for m not equal to n, and then otherwise?
Otherwise 1 for m is equal to n, sir. It becomes multiplication in time domain.
Not.
What is that?
Yeah, he's saying including 1 by 2 pi. He's saying, sir, 2 pi. That integration part will come 2 pi, and after cancelling 1 by 2 pi, it becomes completely whole 1.
And if m equal to n, okay, 0 else. Correct? That's what you told. Correct? Am I correct? I think
Yes,
who told?
yes, sir.
Yeah.
Yes, sir.
Right. So does anybody support this or differs with this? Haribabu.
Yes, sir.
Is
I
correct or
support
not?
it because it's correct, sir.
Yeah. So on which property, because of which property you are able to write this? Assume that
Orthonormal
this is
properties,
correct.
sir.
Which are
Orthonormal properties.
orthonormal? Of what?
Exponential of different frequencies, sir.
Orthonormal property. Yeah. So different say exponentials So e power j, yeah, different frequencies. Finally, when we consider with different omega, this is with say omega e power j omega m as one frequency, e power j omega n as another frequency exponential. Okay, both are orthonormal in fact. Okay, unless you they're orthogonal. If that is why if m equal to n, then only they will be fully correlated. Okay, if m is not equal to n, their correlation is 0. Okay, or projection over another is 0, even if you think of vectors as well. Okay, fine. Is this clear to all? Is this clear to all or not?
Yes, sir.
Yeah.
It's clear.
I can write like this: delta of omega m minus n. That means when omega is equal to, so then this will be there, even d omega is also there. Okay, so in fact delta of d omega, if I knock out, delta of m minus n, that's all. Okay, so because it is 1 for m equal to n. Okay, otherwise it is 0. Yeah. Then what is the final result? Considering this, what is the final result? Okay, is this correct, whatever I have written? So then what is the final result with this? Summation over m and n, x of n into x star of m and delta m minus n. So what will happen then? Yeah, one of you can't you answer? What is now the final result here? No answer I'm hearing.
Sigma x of n whole squares. Yeah.
X of n mod, okay, or x of n into x star of n. Because only when m equal to n, this is 1. Otherwise, say one summation will go as it is. Okay, another summation of m, if you go for different values of m, it will be non-zero. Only when m equal to n, it is 0. Okay, so one summation you can take, one summation with m when you do. Okay, it is non-zero, only m equal to n. This implies that this is x of n whole square. Fine. So that's what is this. Okay. I hope this is clear to you, right? Okay. Fine. So fine. Now we will let us go for the discussion on other kind of properties. Okay. So where we are trying to analyze the properties of x of n. Say if I say that x of n is say real, what does it mean? X of n is real means x of n. So if I write as x real of n plus j times, okay, x of imaginary component of n, then x imaginary component of n is 0. Okay, and x real of n is equal to x of n. Correct? Okay, you have only when you have this sequence is real. Okay, I hope this is clear, right? What do we mean by say x of n is even? Okay. Okay, we are trying to see some properties of sequences and their implication in frequency domain. Okay, yeah, right. So if what do we mean by x of n is even sequence?
X of minus should be equal to x of n.
X of n equal to x of
minus n.
X of n equal to minus x of minus n. That is sorry.
Okay, you are able to see screen now?
That is odd.
Yes, sir. X of minus n equal to x of n.
Yes, sir.
Okay. X of n equal to x of
minus n. Minus n.
minus n.
Minus n.
Okay. So this is even sequence we are saying. Fine. So now see, say if I give you some sequence x of n. Okay. X of n, say I will give some sequence u of n. Okay, plus j times some delta of n. Okay, assume that I have given this sequence. Okay, find even part of x of n if I say. Okay, what will you do? Say x even of n.
X of n plus x of minus n by
X of n plus
Yes.
x of minus n by
X
2.
of minus n by 2.
X of minus n.
okay. See, if the sequence x of n is real, then this is fine. But if sequence x of n is not real, then how do you define this? Is the same or
Yes,
different?
sir. It will differ. We have to take conjugate
No,
instead
sir.
of x of
X
minus.
of minus n would be conjugate.
So this is also there or not?
Yes, sir. In X.
Here also this will be there.
Even part also, sir. Right.
Plus x star of minus n by 2. Okay, this is what you get the even sequence. So just to check it, okay, just to check whether this happens or not, what we can do is we can substitute here. So u of n, okay, plus, for example, before, without this star, if we substitute, we could have seen the implication. Plus, so what should I write here? U of minus n. Okay, then what should I write here? What should I-
Minus j.
minus j del of minus n. Okay, by 2. Fine. This is equal to u of n plus u of minus n by 2 minus j times del of n minus del of minus n by 2. Okay. So now, see if I sketch it. So how will be x even of n? So real part alone if I sketch. Okay. X even of n.
Sir, that's plus j times del of n minus del of minus n.
All right, very good. Okay. Fine. Now, so if I sketch it, what is difference between x of n and x even of n? Say if I wish, say if I want to visually look at it, so here say assume that I would like to have x even of n and x of n. So what is the difference between them? So just verbally, if I want to tell, what is an even sequence? What is visual? Say, I want to first, okay, real part. Okay, then we will go for the imaginary part later. Okay, so real part if I want to sketch, how will be x of n?
It is symmetric.
Correct? Yeah, I have not plotted the discrete one, but assume that it is discrete. Okay.
Yes.
Okay, so now this is 0. Now, how will be the x even of n? It will be real part. At 0, you have double. Okay, what is the difference between them?
Even part is symmetric about origin.
It is symmetric. Okay. In general, sequence need not be symmetric, but even part is always symmetric. Okay. What about the phase? Sorry, what about the complex term? Oh, so complex part. Sorry, imaginary part. Imaginary part is here delta n. Here it is 0. So it's also symmetric. Okay. So you can see that both will be symmetric in even signal. Okay. So this is just a to give a like recap of the definitions. Okay. We will see we will see these implicate like in the Fourier transform. Okay, if we have some partial information about the signal in time domain, how does its information in frequency domain can be reflected or can be captured? Okay, so now let us say take so x of n. So before we move on, say assume that we want to find Fourier transform for some variations of x of n. For x of minus n, what do you think is Fourier transform? So again, how do you do this? If I ask you to find this, how do you do this? And what is the answer? Quickly do and tell me the answer. If you know directly, otherwise do and tell.
X of e to the power minus j omega.
X of e power
Minus j omega.
okay. Right. So what is x star of n? Discrete time Fourier transform. X star of n. That is, see, please note that all through x of n is complex signal. Okay. So we will go and we will state specifically when it is real signal. Then what is Fourier transform? Discrete time Fourier transform. Yeah, you can do and tell again. Some of you, some of the other student is requested to tell. Yeah, request one of the army officials to tell. So how do I derive first? So if I want to find it out, what is its discrete time Fourier transform? Well, how do I do? How do I proceed? Girish, if you are there. Pradeep, both are not there. Manmeet,
Sir, we'll go by the definition of the x e to the j omega, sir.
Yeah.
And sir.
Can you quickly derive and tell? Say I will take this one as x1 of n. Okay, just to be simple. I want to find transform of this just the notation for discrete time Fourier transform here. Okay, x1 of n. Okay, sir. I will go to the definition. I will apply the definition. Okay, sir. X1. Okay, e power minus j omega n and so on. Okay, so over n. Okay, here, sorry. Yeah, now I will substitute explicitly for x1 of n. Sir. Now tell me, what should I do? I got up to here. Then what should I do?
Sir,
see, if there is a star here, I don't know what to do. Okay, so I will take star outside. Fine. Sure. If I take star out, how do I write? N equal to minus infinity infinity. X of n e power. If I take star outside like this, okay, what should I write here? E power
j omega n, sir.
Yeah, j omega n. So what is the answer now?
This is the Fourier transfer, sir, of xn.
What should I write? X star. Okay, what should I write inside?
E j omega, sir.
E power j omega can I write? If I write e power j omega, will it be sufficient? Because see, x of n e power minus j omega, and if it is there, then e power j omega I can write. Sure. Otherwise, now what should I write? X star
of e raised to power minus j omega, sir.
Yeah, minus j omega. Fine. Okay, this is all. Okay, so now let us move on. So I just want to find Fourier transform of even part of x of n. What is it? Okay, I just wish to find. So discrete time Fourier transform of x even of n is equal to. Some of you know the answer. I hope some of you must know the answer. What is the answer?
X of e power j omega plus j times x conjugate of e power j omega by 2.
Yeah, very good. So if we want to derive, what we do is x of n, okay, plus x star of minus n, okay, by 2. This is the how we write the definition for x even of n, right? Okay, x of n plus x star of minus n by 2, correct? This is the definition for x even of n, right? So now I will substitute this. Okay, this is equal to what? This is equal to Fourier transform of, sorry, Fourier transform should I write? I would like to skip Fourier transform now. Equal to what? This is equal to
X of e power j omega by 2 plus
x of e power omega plus
x conjugate of e power j omega.
Written explicitly x star of minus n. What will be the Fourier transform? Okay, you can see that it will be x star of e power j omega. Okay, so in fact using these two also you can see. Okay, x star of minus n, if you write here, it will be minus will get cancelled, x star of. Okay, right. Okay, what is this? So probably I will write it here instead of here. Okay, I will end it here. This is equal to, sorry. What is the answer? I am not able to hear still the answers from you. This answer for this.
Real part of x of e to the power j omega.
Because x of e power j omega plus its conjugate, right? So this will be equal to real part of x of e power j omega. Please note, real part is different from even part. Okay, so I hope you are clear, right? Hope you people all are clear on that. X real of e power j omega. Okay, is this fine?
Yes, sir.
Similarly, you can see that x odd part of n, discrete time Fourier transform, will be equal to what? Odd part will be equal to
x of n minus
what?
X of e power j omega.
What is that? Pure j omega.
Yes,
Odd part
yes, sir. Odd part of the Fourier transform.
is what?
J into imaginary part.
X of e power j. Imaginary part of this it will be. Okay. J into will come. So we will write in the next space. Okay. So Fourier transform of x odd part of n. Okay. X odd part Fourier transform, if you want to write, x of n minus x star of minus n. Okay, this is how we define the odd part. Correct? This is equal to x star x of e power j omega minus x star of e power j omega. Okay, by 2. And this will be j times x imaginary part of e power j omega. Correct? Hope this is clear. This kind of derivation. Okay, you need not even explicitly go into the first principles or two definitions. Okay, since you know, if you know these small identities, then you can easily do this. Okay, in fact, these all can be quite easily and comfortably derived yourself. Okay, just once you should understand and do that solve. So then say now let x of n be real now. Okay, that means what? What do we mean by x of n real? X of n is real means? What do we mean by x of n real? No answer? See, those who which you know
It is
quickly.
not. It does not have an imaginary part.
Imaginary
Yeah, it
X
doesn't.
conjugate.
But if you want
It
to
is
write,
purely,
X conjugate of n.
it is purely real.
right, it is purely real. Okay, be real means x of n equal to x star of n. Correct? This implies what? In frequency domain. This implies what? X of
E power j omega equal to
x
of
e power. This
minus
is what is referred to as what?
conjugate symmetric form.
It's symmetry. Okay. Okay, this is referred to as conjugate symmetry. Fine. Now, say given this, what can you tell about the x of e power j omega? So I just want to find, it is given that x of n is real. Okay. So I want to find the Fourier transform of x of n. Find Fourier transform of x of n. This is as if finding Fourier transform of, okay, x real part of n. Correct? Because x of n is anywhere real. Okay. So how do I find this? Fourier transform of real part, how do I get? X of n so our,
Sir, here x of n is real now, sir.
yeah,
Or it is complex.
yeah, x of n is real. Directly, in fact, we'll make use of this. Okay, so if x of n is real, what more can we tell about the frequency, like the Fourier transform? So let us apply Fourier transform here. We got already this. Given this conjugate symmetry, what can you tell more about the spectrum? This implies what? If this information is given, so I can write this as, see, I will split this as x real of x e power j omega. Let x of e power j omega b is equal to x real of e power j omega. Okay, minus j times x imaginary of e power j omega. Okay, if I give this information to you, okay, so what does this indicate? What does this say? Let this be 1. What does 1 indicate? What does 1 indicate? So x of x real of e power j omega minus j times x imaginary of e power j omega is equal to x star. So x real star e power j omega minus j times real star is what? This is anyway real component, right? So you people
But
are
actually plus j.
Yeah, no need to write star here. Correct?
Yes, sir.
Yeah, minus is there.
And
X.
here we will get plus j on the right hand side.
Correct? What I have written is correct or not? What does this indicate? So you know the properties, right? So xr of e power j omega is equal to xr of e power minus j omega. What does this indicate? And x I of e power j omega is equal to, sorry, here plus, is equal to is equal to what? Minus xi of e power minus j omega. What are these implications? What are these telling? I have written something here, right?
Magnitude is
Magnitude is
even.
Magnitude is even. Magnitude spectrum is even or symmetric. Okay, phase spectrum is
Odd.
real part is even. Okay, and imaginary part is odd. Okay, here it is not purely telling about magnitude. You can also write this, okay, in terms of magnitude and phase. Then you can tell that magnitude is even and phase is odd. Okay, or you can also tell that here real part spectrum is even and imaginary part is odd. What I'm writing correct or not? Hello, you are there?
Yes, sir.
Yeah, you are able to
Yeah,
understand.
yes, sir.
Yeah. So if you say that the signal is real, then then you can say that the real part of the spectrum is even, imaginary part of the spectrum is odd. Say what more can you tell? Say if I give x of n is real, so what more can you tell? Say x of n is equal to x of n. Say if I give you any complex signal, okay, if I want the real part of the complex signal to come, okay, how do I get? I just want to identify the real part of the complex signal. So how do I identify?
Fourier transform of even part of the
Can I write this or
signal.
not? X real of n equal to x of n plus x star of n by 2. The real part of any signal, say if I just, even if x of n is not real, okay, not necessarily real here.
Yes, sir.
Okay, for any x of n, so real part of signal. Can be written like this, right? Is this fine or not?
Yes, sir.
So now if you want to Fourier transform of real part of the signal, what should I do now? How do I express Fourier transform of x of n plus x star of n? So what is this? Yeah,
Even.
e power j omega plus
E power j omega plus
x star of
star of e power minus j omega.
by 2. And what is this?
Even part of the spectrum.
This is the x even of the spectrum. Okay, if we want to find the Fourier transform of the real part, okay, so x real of n DTFT is x even of e power j omega. Okay, so similarly x odd part of n DTFT is what?
Imaginary part of x of n. This,
This imaginary part of x of n is
odd part
x.
of spectrum.
Okay, just check with J what will happen. So if we Fourier transform of x imaginary part of n is equal to Fourier transform of Yeah, x of n plus x minus some way. Yeah, just take care of j term. Okay, my minus x star of n, right? By, okay, 2 here. So imaginary part purely, if you want to tell 2j, let us take 2j. Okay, so in that case, this is equal to 1 by j, and this is nothing but same thing with minus will come, so which is odd part, so minus j times odd part, correct? Hope you people are able to understand what I'm writing here. You want me to write explicitly? Manmit, you people are following?
Sir.
You people are following?
Sir.
So what will come now? So I'm just writing corresponding Fourier transform x e power minus j omega. Okay, x star by 2. Okay, and this is equal to, see, this is x odd part e power j omega. But actually 1 by, yeah?
It will be divided by 2j, sir. Sorry, 1, right.
So 2j, I have written 1 by j, so it is minus j times. Okay, so you can write like this, or you can just take j this side and then j times imaginary part. Otherwise, is simply equal to x sort of. Okay, you can write like this.
Sir.
Yeah, right. Fine. So like this, you can. What I suggest is, you look at all these properties, derivations, okay, from your side, because these are very important, not only for say understanding what will happen in frequency domain if some operation is done in time domain, but these properties will see in many of the problems. If you want to say tell what is its Fourier transform, okay, what is the frequency response, okay, if I make some change to the time domain signal, what will happen in the frequency domain? What will be the output? Because of the change, I might have done something at the input. So for all these things, these properties forms very important part. Okay, so you should be able to very fairly apply these properties to solve the problems of reasonably complicated problems. Okay, especially wherever there is a modification to the input, if there is a variation of the signal, okay, so if you are able to relate them to some of the properties of some simplified signals, you can easily find their outputs. Okay, similarly with other in other applications. Okay, so I suggest you be clear on this. Here, one thing we didn't specifically write is similarly here you can show that the phase magnitude spectrum is symmetric and phase spectrum is antisymmetric. Okay, hope you know that, but I think I will so you can see this actually. Okay, so you just find mod, because mod with star and without star is same, right? So it is symmetric. Okay, phase spectrum, when you see this will be negative angle will come. So star conjugate will give minus of angle. So you write x of e power j omega as magnitude and phase. Then you just show yourself this. Okay, see yourself this. So is this clear? Whatever I have written here very crisply. Is this clear or not?
Yes, sir.
No. Is this clear?
Yes, sir.
Yeah. So especially those who have not derived before, just see x of e power j omega. You can write it as x of mod of x of e power j omega plus angle of like I have written before. So if you just write x of e power j omega, okay, is equal to mod of x of e power j omega, okay, into e power minus j or plus j phi omega. Okay, just write like this. Now what you do? X star of e power minus j omega. What it will be? You just write. Okay, then you will get these two properties. Okay, so this I have not derived fully. You can consider it as a homework if you want to specifically take it as homework. Okay, this homework. Okay, fine. Derive this, and few more things I left in between. Okay, I have not derived explicitly this one. Okay, this also I have not derived. Like that, here and there, wherever I have left, you people complete them. Okay, understand these better, and we will try to solve some problems based on this, probably in the next class. Okay, thank you then. So if you have any questions, you can ask. Otherwise, we will stop the class now. Any questions?
No, sir.
Okay, fine. If there are no questions, I think we can leave the class. We can stop the class. Yeah. So
Yes.
Keep going. We'll meet again on Friday. If I am able to send some video lecture before Friday, you assume that there is no class. Okay. So I will intimate explicitly that no class. If I'm not, if I didn't send anything or some, if I couldn't send anything, make sure you assume that class is there and please come to the class. Okay. So no need to explicitly tell every time.
Yes,
Okay. Okay.
Right. Thank you, sir. Good afternoon, sir.
Yeah. Good afternoon. Bye.